This is a lesson about periodicity and symmetry of functions. And the first thing we'll deal with is the period of a function. And the period is the distance that a function, the graph of a function, travels horizontally before it repeats itself all over again. So you'll see a shape repeat over and over and over again, and each interval that shape's contained in is a period. So for circular functions, cosine and sine, the period is 2 pi. It's the radius of the unit circle. It's the circumference of the unit circle. So let's take a look at the cosine function and the sine function, and we're going to graph these just using the quadrantal coordinates here for 0 or pi radians, pi over 2, pi, and 3 pi over 2, with the x-coordinates of those being cosine and the y being the sine. So the cosine of theta, as you notice, the cosine, the x-coordinates, never go above 1 or below negative 1. So on my y-axis, I'm between 1, positive 1 vertically, and negative 1. So the y is going to be, the y value will tell me what the value of the cosine is at those points. And we can get all of our special angles in here, and we can see in class how that makes this a nice curved function. But basically we can plot the key points from the unit circle here. So we already said that the period of both cosine and sine is 2 pi, because once you've gone all the way around the circle 2 pi, these values just repeat themselves over and over and over. So if I take the period, and I'm going to go from 0 to 2 pi radians, so radians is on my horizontal axis, and I'm going to divide that into 4 even intervals. So this will be pi, pi over 2, 3 pi over 2, and I'm going to plot the value of the cosine function at each of those. So at 0, because this is 2 pi or 0, the cosine is 1. So cosine starts up here. And then at pi over 2 radians, cosine is 0. At pi radians, cosine is negative 1. So at pi, I'm at negative 1. At 3 pi over 2, the cosine is 0 again. And at 2 pi, the cosine is positive 1 again. And you're going to see this pattern from top to middle to bottom to middle to top over and over again. So when I move left, and I take this same interval, and I divide the negative 2 pi here, so this interval of 2 pi, and I divide that up, it would be like moving this way. So at negative pi over 2 radians would be a clockwise turn like so. The cosine is 0. At negative pi radians, the cosine is negative 1. At negative 3 pi over 2 radians, the cosine is 0. And at negative 2 pi radians, which is all the way around, again, the cosine is back to a positive 1. So now we can connect all these points, and we do it with these smooth curves that inflect at these points. And this goes from looking like it's concave down to being concave up. So these look like little cups, and they're smooth. And you could see that if you could box this area and just slide it over here, that the whole thing just repeats every 2 pi. So now we'll do the same thing with the sine function. Again, the sine of the y-coordinates of these points, and sine never goes above 1 in the parent function or below negative 1. So the y values will be the value of sine at each point along here. We'll divide this up the same way. Into 4 equal parts, so this will be negative pi over 2, negative 3 pi over 2. So sine at 0 radians, the sine is this value here on the unit circle. It's the coordinates are 1, 0, and the y-coordinate here tells us the sine. So sine goes through the origin, the parent function. At pi over 2, the sine is 1. At pi radians, the sine is back to 0. At 3 pi over 2, the sine is negative 1. And at all the way around at 2 pi, the sine is back to 0. And then on the other side, if we go negative angles, so when I want to go to negative pi over 2 radians, I go this way on the unit circle, and the sine is negative 1. So it's different than cosine. It doesn't It's not symmetrical about that y-axis. So then at negative pi radians, the sign is back to 0, and at negative 3 pi over 2 radians, it's back to 1, and then at negative 2 pi, it's back to 0 again. So this function, the sine function, looks like cosine function just shifted to the right by pi over 2 units. So my cup is here, and then I turn and I'm like so, and that continues, you know, infinitely. Both of these continue infinitely to the right and infinitely to the left. Okay, so that's the cosine and sine, both having a period of 2 pi. So now we're going to talk about odd functions and even functions, and we'll come back to these in a few minutes. But these are basically the parent function for cosine and the parent function for the sine. Okay, even and odd functions. Basically, even and odd functions look differently when they're graphed. Even functions are symmetrical about the y-axis. They have what we call y-axis symmetry. Every point on the right-hand side of the y-axis is reflected across the y-axis to a point. So let me get this one filled in. If we look at, this is the graph of y equals x squared. So if I pick a point on this, like 2, 4. Okay, so when I put in a 2, my function is 4, because 2 squared is 4. Okay, the attributes algebraically of an even function is that when I put in the opposite x value, I get the same y value out as this original point here. So if I put in a negative 2, when I'd say y equals negative 2 squared, I get my same original y value. So two opposite x values will have the same y value, and that's the attribute of an even function. And you see how you get this symmetry. You could put a ruler through those going across the y-axis, and this perfectly reflection of all the points. So I think of this as opposite in, same out. Odd functions have what we call origin symmetry. They are symmetrical about the origin at this point. So an example of an odd function would be y equals x to the third, a cubic function. So maybe I pick a point on here like 2, x is 2. When x is 2, 2 to the third is 8, so y is 8. So now when I try putting in the opposite of 2, when I put in negative 2, well, if I take negative 2 and raise it to the third power, I'm at negative 8. So negative 2 to the third power is negative 8. So I get this when I put in the opposite x value, I don't get the same y value as I do up here. I get the opposite y value. So the opposite input gives me opposite output. And so what happens is these points, this is like a full 180 around. This is reflected, this point is reflected across the origin down to here. So if you want to, you could always take a point and its opposite point with two opposite x values, and you'll always, if you draw a line through them, that'll always go right through the origin. So origin symmetry is odd, y-axis symmetry is even functions. So let's just go back to sine and cosine, which is a big deal on this. And if I look at cosine real quick, I can see that this is an even function because this has y-axis symmetry. I see this point's reflected across here. Every point is reflected across. If I take pi, the value of the function is -1. If I take the opposite input of negative pi, I get the same. I'm at the same place, -1. So that's an even function. Sine, I can easily see, is an odd function. It has y-axis symmetry. This point is reflected across the origin down to here. So when I take the input value of pi over 2, the value of the function is 1. When I take the opposite input of negative pi over 2, I get the opposite y value of -1. So I can see across the origin that that this is would be classified as an odd function. So that's something you got to remember. Cosine's an even function and sine is an odd function. with respect to the y-axis and respect to the origin. So let's just do a few examples to look at algebraically how to tell without graphing if a function is even, odd, or neither, because many functions are neither even nor odd. So this is a function, and without graphing it, what I'm going to do is find out what's the value if I put in the opposite x value. So everywhere that x is, I'm just going to substitute a negative x. So when I do that, I get, in this one, negative x when I square it is still a positive x squared. And when I raise the negative x to the fourth power even, it's a positive x to the fourth plus 1. Well, then I look back at this and I see that it's the same. Okay, it's the same as the original function. So what I've just proven is that f of negative x is equal to f of x. So I put in the opposite input and I get the same output as the original function. So that would make this even. Okay, the next one, part B, I'm going to do the same thing. F of negative x. So where there's a x's, I put in negative x's. And I simplify. When I raise a negative base to an odd power, it becomes a negative. And this is negative 4 times negative x, or plus x. And I look up here, and I see that this is a negative when that was positive, and this is a positive when that was negative. So to make it really clear, if I could just factor out that negative and show that this is the original function, and this tells me it's the opposite of that. Okay, so quite literally, these two are opposites. One's positive and one's negative. So quite literally, f of negative x, when I put in an opposite, a negative x, it made the value of y negative. So I got the opposite result. So this is an odd function. Okay, and then this last one, put in a negative x when I square it, plus negative x. So this is a positive x squared minus x. Now I look back up to the original, and I see, well, the x squared, those are the same, but these are opposite. So this would be neither even nor odd. It has to be exactly the same, or as the original function, or it has to be exactly the opposite, meaning the opposite sign. Okay, so then the last thing I want to do is a little example of how to graph. There's some exercises in your textbook, but just the idea of how to graph an even or an odd function. I'm given a function where I'm told the period is 4. So it goes from 0 to 4, and then it's going to, repeat. So the period is 4 long. So if this function is even between negative 8 and positive 8, if I continue this over to 5, 6, 7, 8, it's going to repeat that shape again. So if I just want to see what point this is, this looks like it's at 2, 3. So I'm going to put that point there. And I'm going to come up and go like so. And then the point that's halfway between 4 and 8, which would be 6, 3 would be on that graph too. Okay, so to make this an even function, it has to have y-axis symmetry. So it has to look the same on the other side. So that means if I input a negative 2 right here, I should also get a positive 3. So this function looks like this on the left, and then you can see your y-axis symmetry. These points are reflected across, and then I'm going to go up, and this will go to negative 8, and this will be the point negative 6, 3, and this was the point negative 2, 3. So you see where I have the opposite x values, I'm still at positive 3. Okay, now I'm going to take that same original function and complete it as if it's an odd function. So again, the period is 4, and this ordered pair, this is 2, 3. So if this is an odd function, when I put in a negative 2, it should give me back a negative 3 in this function. So that's going to be down here. So if I go down to negative 3, that will be on the graph. So I can go like so. Okay, and if I have to continue to repeat this function between -8 and +8, it doesn't, we don't really, we could kind of draw it two ways. So I'm just going to, I'm going to make it look like this and come up to 8 here, and this will be at the point 6, -3. So if I look at on the other side here, I go to -8, so this is +8. The point -6, +3 would be on the graph, so that would look like so. -6, and then the opposite input. So I could finish it like that, or I could make this go like so, and make this go like so. So I got sort of a choice on that one. So anyway, you see this has the y-axis symmetry. This is odd, and this has the this has the origin symmetry. This is odd, and this has the y-axis symmetry. This is even, and that's it.